Hello and welcome to yet another video of Cornerstones of Math. In this video, we are going to find the function ft defined on the set of real numbers satisfying integral ft dt from 0 to tangent x is equal to e to the power of x minus 1 for all real numbers x in the interval negative pi over 2, pi over 2. I will show you two similar but slightly different methods to do that. And as you saw from the thumbnail, both methods heavily rely on differentiating the function rather than integrating them. Let me explain this in more detail. In the first method, the very first thing that I'm gonna do is to introduce the antiderivative of function ft because we need that. So let capital Ft be the antiderivative of the given function ft. Then the fundamental theorem of calculus allows us to write the left-hand side as capital F of tangent x minus capital F of 0. So this equals e to the power of x minus 1. Now let us differentiate both sides with respect to x. When differentiating the left-hand side, we have to apply the chain rule. So first we have small f of tangent x. And by the chain rule, we have to multiply the derivative of tangent x, which is secant squared x. And this f0 is just constant, so it gives 0. And if we differentiate the right-hand side, we simply obtain e to the power of x. Therefore, f of tangent x equals e to the power of x divided by secant squared x, which is e to the power of x divided by 1 plus tangent squared x. Here I wrote the denominator as 1 plus tangent squared x because we have to make a substitution tangent x equals t to find the function ft. Then we have x equals arctangent t, which gives the range greater than negative pi over 2 and less than pi over 2, which is the same range given in the problem. Then we have ft equals e to the power of arctangent t divided by 1 plus t squared, and since t equals tangent x, it can have all values from the real number set. In the second method, I am going to make a substitution before doing anything else. That is, let us think why this equation looks rather complicated at first glance. Mainly, it is because there's this tangent x at the upper bound of integral. So let us simplify that part to see what happens. Let tangent x equals u. Then, since it is given that x is greater than negative pi over 2 and less than pi over 2, which happens to be the range of the arctangent function, we can say that x equals arctangent u. Then the equation becomes integral from 0 to u ft dt equals e to the power of arctangent u minus 1, which is satisfied for all real numbers u. Here we can write the left-hand side as capital F of u minus capital F of 0 and do the same thing. But the derivative of the left-hand side is actually one of the most famous properties of calculus that many of you simply memorize this as a formula. So if we differentiate with respect to u, on the left-hand side we simply have fu, and on the right-hand side, by applying the chain rule, first the derivative of exponential function, so e to the power of arctangent u, times the derivative of arctangent function, which may be not familiar to some of you, but I think many of you already know that it is 1 over 1 plus u squared. Well, if you do not know why, just take a quick look at this derivation. Anyway, we have essentially found the function f. All we need to do is to simply change the variable into t, then present the answer as e to the power of arctangent t divided by 1 plus t squared, where t can have real values. Fun fact, you can visually check your answer by plotting two graphs. One, the left-hand side function, integral ft dt from 0 to tangent x, and the other the right-hand side function e to the power of x minus 1. And that's all for today's video. Thank you for watching. Please don't forget to hit that like and subscribe buttons if you enjoyed this video, and I will see you in another video.